Hello guys, I hope you can hear and see me well. If you can, please type something in the chat. And welcome to this YouTube live. So allow me to introduce myself a little bit. So I am Hassan Abdul Sawoor. Right now it should have started. Right now it should have started. I see one comment in the chat asking when it's gonna start. So you should be able to see the stream right now, hopefully. If not, please let me know. I hope. Right. So what are we gonna discuss today? So I'm gonna introduce like a little bit about my background, and then we're gonna talk about one nice data set that is quite large, about 3 million cars. So it's a simple problem, and our goal is going to be like how to predict the prices of these cars, right? So let me share my screen. Actually, screen one. Let me allow share system audio. Yeah, that should be fine. All right, good. Can you see my screen? Great. Okay. So let me try to maximize this. Oh. So I am an Abu Dhabi University alumni. I graduated from the Bachelor of Information Systems Technology. And after graduation, I worked in the IT department as a software developer or programmer, if you want, and in the operational planning and strategy department as a data analyst. Currently, I am a data analyst at New York University, Abu Dhabi, and I am pursuing my master's degree in data science from Georgia Institute of Technology, right? So this is just a little bit about myself. Um, so now let's go and talk about our data set, okay? So our data set, this is our data set. So the idea is we have a bunch of cars, right? And we want to predict a fair price for these cars, like how much is a car going to cost us, for example. So imagine you're going to buy a car and you want the computer to answer the question for you. Is this car that I'm buying, is it a fair price? Is it a good price? How much should I be expected to pay based on the color, condition, and all? So in order to be able to do something like this, we need data, we need information on cars. And so what I have here is a data set on this site called Kaggle. And this is a site for data sets, right? So if you want any data sets to play with, you can come to this site and they organize competitions and all. And you can, for example, take part in these competitions. You can see the results. So competition ended, who won, and all. And you can see, for example, so houses. Data set, you can choose medium or large. So yeah, Hogwarts houses. Okay, this maybe a Brazilian e-commerce public data set. House prices 2023. I think this is a real one. So this is another example. You can see like the details about the data set, and you can download the data. You just need to create an account. Account is free, does not cost money, right? So you just create an account and then you can download the data. And here also under code, you can see what did others do based on this data set. So some people, they will take this data set, they will write some code for ADA or exploratory data analysis or machine learning, whatever, and then they upload the code, and then you can discuss it with others and so on. And you can see a view of the data here, right? So this is the site. Okay, it's a nice site to know if you want to do a project, undergrad, or just to give yourself more knowledge in the field of data science or something. So you can come and take datasets from here, and there are pretty good datasets. So the dataset we have today is for cars. So let me show you a little bit about the dataset. So we have the car makers of Ford, BMW. We have the model, and as you can see right away, oh, there are some missing values. So I have a BMW, but I don't know the model. Now, the reason this information is missing in this particular dataset, and if you read this card or this information about the dataset, you'll understand why. The reason it's missing is because this was collected from advertisements. So imagine, for example, here in the EU, there are websites that will list cars. So this data was collected from similar websites that list car advertisements using software. Software that does this is usually called web crawlers. So this software does a pretty good job, but not a perfect job. So as you can see, there are some missing values. So whenever you are going to start working with any dataset, you will have to keep this in mind, right? You will have to take into account how good the data is. Because if you want to do any machine learning or any prediction, and today mainly we're talking about regression, which is a prediction of numerical values, so you can predict car price, house price, how much rain you can, or how powerful, God forbid, an earthquake is going to be. So all these are numerical predictions. So, and usually and fall under the broad umbrella of regression. So not just linear regression. There are a variety of regression models, and we're going to see some today. But the first thing before you do any machine learning is you have to clean your data. You have to make sure that the data you are feeding the model is coherent, is reliable, and you resolve issues such as these. Or you find a model, right? You find a model that can, work with such issues, depending on what you're trying to achieve. You might want to get rid of rows that has no values in the maker model. You might fill them with the most common values if you know something about the data, if you have some expert opinion. But this is a general idea. So you have the maker, the model, the mileage, the manufacturer year, and the engine displacement, the engine power, the body type, color slug is just color. Stock year is just the year the car was inspected for carbon emission. Transmission is the transmission type, manual or automatic. Door count is the number of doors. Seat count, the number of seats, fuel type. And the price, the most important variable, that's what you are trying to predict. And the date the advertisement was created, the date the advertisement was last seen, right? So this is the information that you have, and then when you download it, so it's a pretty large Excel file. I have downloaded it here, so it's around 500 MB, right? If you have any questions, Guy, please feel free to post them in the chat, right? So I have downloaded the dataset here. Yeah, so this is the CSV file. Now, you can try to open this with Excel, but I wouldn't recommend that for different reasons. Okay, first, because it's really large. Your computer might not have enough memory. Excel might freeze. So usually when you have such a large data sets, I'm going to see this. we want to deal with it or explore our data in a different way, right? So not just Excel. Okay, but if you have a small file, so 5 MB, 2 MB, kilobytes, then you can open this with Excel, no problem, right? So let's go back here. So the work I did for this it was part of a machine learning course I took in Georgia Institute of Technology, right? So now that you've downloaded the data, right? Now that you've downloaded the data, I'm just gonna walk you through some examples of how we are going, of basically how I did some cleaning on the data. Now, so the effort, so this was a group project. The effort for this was split on a team of 3 people. So I'm just going to show you the parts that they did, right? But keep in mind that what the project entailed more work, much more work than what you are seeing today, right? So if you are not familiar with Python, because I've seen some people say they are not familiar with Python, all right? So Python is a programming language, right? Just like any other programming language, okay? So you can go to Python, right? You can Google and then you can download. You can download for Linux, for Windows. Do they have Linux? Yeah, they should have Linux. Other platforms. Yeah, so you can see the different versions here. So right now, the latest version is 3.12. I don't recommend you download 3.12. I recommend you download 3.11. So just a little bit about Python. So they it's an open source programming language, and the people who they have this community that's responsible for evolving the language and all. So uh, the people in charge of evolving the language have been making a lot of big changes between the versions. So 3.10 is drastically different from 3.9, 3.11, some big changes, again 3.12, and right now 3.13. This is a pre-release, so I don't recommend you download this. So my recommendation is, when they release 3.12, some people who are in the open source community did not get a chance to update their software they built using Python on 3.12. So that's why I'm recommending you just stick to 3.11, right? And so once you download it, it's just a regular installer. You can just install it like any other language. I have it installed. And the software that I'm using today is called VS Code. This is the software, Visual Studio Code. So VS Code is an IDE, integrated development environment. It's just a nice software that allows you to write Python code. So here I have a nice feature called Jupyter Notebooks or Visual Studio Code Notebooks. Okay, so if you Google Jupyter Notebook or Visual Studio Code Notebooks, you're gonna see almost the same thing. So it's just a file. This cleaning is just a file. I have it here, right? But it combines some comments, text, if you want, description of what you're doing, and together with code. And you can see the results of running this code, for example. So as you can see here, this is an overview of the data, right? So if you want to get Visual Studio Code, you can download it. Again, it's free. You have it on Linux, Mac, and Windows. You can download it here, and it's not just for Python, it's for all other languages you can think of. So, and it's a pretty good software supported by Microsoft, so they update it frequently. Right? Now, so in Python, there are some famous libraries called pandas and NumPy, right? And I'm going to give you some heads up here about each library, what it does, why is it important. But I truly recommend that if you want to learn and apply data science, you need to go and explore. So learn pandas, and the best way is to learn by practice. So take an example data set and try to apply something on it. So for example, how do I read the CSV file, right? Using pandas. So pandas is basically an Excel in Python if you want. So rather than opening your Excel and just start playing with your data, you can do the same with pandas using using Python, right? But it's much more powerful, and certain things are easier done in pandas. And of course, you get the automation. So you do it once. Well, the stream. Yes, I think. Sorry, I got a question. So will the stream be saved so we can revisit? Yes, I think so. Yeah. So no worries, Ali. I think. So back. So yes, I was talking about pandas. So pandas is just like a library to allow you to play with your data, right? And all of these things are free, right? You don't need to pay anything, which is good and important, right? We all like free stuff. So you can even look at their software, 10 minutes to pandas, import this. They show you they have some nice code, and uh, feel free to copy the code, play with it. Nothing wrong with that. That's how you learn, right? So I have pandas here. So I'm going to read the data, right? And this is my Excel file. And I specify low memory. So whenever pandas is reading an Excel file, it's trying to interpret what's the column type, right? So when you say low memory is true, it means that if you have 3 million values in a column, it's just going to pick like 100,000, the first 100,000 values, and then like, okay, so they are all numerical. So, okay, good, makes sense. I'm going to consider this column as a numerical column. But when you set this low memory to false, then you're forcing it to consider the entire column when inferring the column type, right? So I read the data, and then I reset what's called an index. Here, let me do this. This is slightly another file. So I have the data here, and this is the clean data. Okay, I'm cheating here a little bit, but this is the clean data, right? After cleaning. So I've already read it, and I'm going to go over this few lines of code. So data is going to print a few rows from the start and the end of your data. If you want to see just a few rows, like for example, you can say head 20, so it will show you the first 20 rows, or you can say tail, again, the last 20 rows, and so on, right? And by default, you see this column. This column is not part of the data. It's like an index, an auto-numerical column created by pandas, right? So when you reset index, you're basically telling pandas, like, drop this index and recreate it from scratch, right? And you can choose to add it as a new column in the data set. So if you just want to add an auto number For every row in your data set, you can just say data.reset index, and that's it, right? And that's what I'm doing here. I'm just adding this column, like add AD means advertisement 0, advertisement 1, right? So I do some initial cleaning. So here is this, for this syntax, I am excluding all rows where we have a maker and we have a model, right? And everything else where we don't have a maker or a model, I'm excluding these. So including rows where the maker and model are known. So BMW i3 or i5, for example, or Toyota Corolla if you want. Okay, and then I choose the most important columns for me. So these are the columns that I'll be building my model on, right? And I just filter on here. I do more cleaning on the price. Okay, so we have found that this price 1295.3 is just a price. So this is an issue that is specific to this data set. So this price just keeps repeating. So it's a random price. It's a data collection issue. But there is a high number of cars with this price, but in reality, this is just a dummy price, not a real price. So it's not a real value. So we excluded all cars with this price. Our cars that are worth less than $500, we decided to exclude them, and cars greater than 50,000, because we found that some cars are like millions, and probably there are cars worth that much, but I don't think like cars with such a high price were a good target for building a machine learning model. Like such luxurious cars like Lamborghini or Ferrari, I mean, these need their own model. You can't combine them with the rest of the data, right? And I continue to do some cleaning here. So here I count how many empty values are in each column. So as you can see, so here nulls 2, null means there are no values actually. So I have these two columns, they don't have a value, right? And then I define a custom function for cleaning the data. I clean the stock here and the body type, right? And then for the engine displacement, I've selected a criteria greater than 600, less than 8,500. If the engine displacement is between 600 and 8,500, that's reasonable. Now, so you might ask, so why these two values? And the answer is you have to do a little bit of research. So when you are cleaning the data, when you are modeling the data, you have to do a little bit of research, right? So that you have to understand the problem a little bit, right? And so there is plenty of code here that I don't want to go over line by line, because these are the easy stuff. So you can create similar code if you want, and you just have to work on column by column. So you take each column of the data. So for example, you start with the maker, you find out what are the issues. So how many cars have no maker, how many cars have no model, for example, and what are the most frequent, what's the most frequent model of cars or maker of cars, whether some values are strange, for example. So for example, if I do something like this, if I do data and this is just how you select a single column from this data frame. A data frame is just, if you hear me saying the word data frame, it's just a fancy Excel sheet. Okay, so think of pandas as Excel, but in Python. Okay, this is the simplest way you can think of what is pandas, or you can understand pandas, right? So, and this is the way, so I add this bracket here, and then I put a column in between two quotes. So this is how I select a column. So this is my column, so it's just giving me this column from my data, right? And if I want unique values, so you can see we have, so this function is going to tell me, so what are the unique values in these columns? We have Ford, we have Rolls-Royce, we have Alfa Romeo, Lamborghini. Oh, we still have Lamborghinis here. Okay, so didn't perhaps they had a reasonable price. We have Mercedes-Benz, Chevrolet, Volvo. So all of these regular manufacturers, and if you want, you can do value counts. So you can see how many BMWs, how many Mercedes-Benz, Audi, Volkswagen, and so on. So these are things that you can do with the data just to see what makes sense and what doesn't make sense. And I encourage you to spend a good amount of time in cleaning the data, because any machine learning model, if you give it reasonable data, if you give it high quality data, then you're gonna get good predictions out of it. But if you don't give it high quality data, then you're gonna struggle, right? You'll find that a car, for example, is worth $2,000 or dirhams or whatever, and your model is saying it's 500. A car is worth 50, your model is saying 20. So these big differences. Now there is a way to quantify the performance of the model, right? And I'm going to talk about how to quantify this, right? So there are ways. So you will find, and the way, one of the most common ways is called R squared, and R squared is basically your model's ability to explain, to capture the difference, or to capture the information that's present in the data. Let's say this way. And if it can capture like 70% of that information, then depending also on the kind of problem you are working on. So if it can capture like 70%, maybe that's good. At some applications, you might want to get to 99%, 90%. Things like the study human behavior, you might be able to only capture like 40%, and that would be like a very high R squared, right? So spend a good time cleaning the data, right? And these are, and most of the time these are logical things. For example, so if you go back here, so the price, if you find that there is a specific price that, like, so how did we determine this odd price that I mentioned before, 123 something? Yes, 1295.34. Oh, we found out that like there is 300,000 cars with this price. So, and that's quite impossible. And how do you know it's quite impossible? First, because it's not like 1 to 100, 1 to 50. No, it's exactly this number. And if you look at the value counts for the other prices, you will find out that the maximum a price repeats in a data set is 100 times, 200 times, right? And that's when you know that this price, oh yeah, this price is not logical. Like you can't have 200, 300,000 cars with this price, right? So then you must exclude these cars, right? So it's more of a logic, and the more you do this, the better you will learn, and you'll become. The more you learn, and the better you will become at cleaning data. And go column by column and see if there are relationship between the columns. For example, engine displacement and engine power, how do they relate, right? Maybe the transmission. So it's not just the column, it's also the relationship between the different columns. You might even want to do some research. So has Skoda, for example, ever produced manual transmission cars? in year 2000. So here is code artery. So is this Octavia model ever been produced in a manual with a manual transmission? That's a question you might want to ask, and you might need to bring in a car expert. Now, for a course for dummy data, you might not need to really bring in a car expert, but if you are doing this in the real world, then you will need like an expert, someone who knows a lot about cars. And I have a question here in the chat. So, there is a way to know when your data has been cleaned sufficiently? It's a good question, actually. I will say the best way to know whether your data has been cleaned sufficiently is to look at your model's performance, right? So ideally, you will go over each column, try to find if there are any odd values, unreasonable values, or anything unusual about a column of data, and then you will look at the combination of columns, and then like you've done some cleaning, maybe you make some visualizations, and you will find that there are lots of visualizations that you can consider for identifying anomalies, visualization to detect outliers, for example, visualizations to detect whether certain variables are normally distributed or not, so like QQ plot. So all of these techniques, you will usually perform all of these, and then at one point you need to try one model, right? You need to try test. You need to take one model. It can be a very simple model, doesn't have to be anything complicated. You test it with your data. After you've done testing it, then you say, oh, I'm getting good results, right? And then you inspect the results, what you got from the model, you compare it to the real prices, you're getting good results. So you've probably done a good job cleaning. But if you're getting bad results, or if your R squared or your measures of performance are not good enough, then maybe you need to go back to the data and understand it more, or dig deeper into the issues, right? And certain models like regression, linear regression, multiple linear regression, and so multiple linear regression. So linear regression, basically, if you are not familiar with what is linear regression, so you have, for example, let's say, a number of doors here. So you have this car's data. So let's say number of doors, right? And then you have here the price. So you have a bunch of data points like this. So as you can see, as the number of doors increases, the car price will increase. But then you might have a strange. So a car with so many doors but a low price. So in linear regression, what you're trying to do is find a line that best represents this data. So that's the goal of linear regression. This is just a very rough way of explaining it, guys. Of course, if you want to apply linear regression, I recommend that you go gain an understanding of what's the intuition behind linear regression and the mathematical formulations and the assumptions of linear regression, because there are certain assumptions, certain conditions to be able to apply this machine learning model in order for it to work properly, right? And values like these, like outlier, or another value like up here in the sky. So these things, they can mess up your interpretation of what's the best line. So for example, instead of fitting a line like this one, which is quite close to the data, because of this point, the best line might be fitted like this. So then obviously, because of these 2 points, because of this point, for example, then obviously this line is not great, right? So these are the ways you know that you've done some cleaning on the data. So model assumptions, you check the model assumptions, you see your model performance, and so on. Okay, so now let's get into some of the really exciting stuff, okay? So I'm gonna do something here in front of you and find this interesting. Okay, so I have my clean data, okay? I have my clean data. Where is my clean data? Look, so this is a 370 megabytes file. It's a CSV file, right? Now, if I try to read, okay, see how much time and second is it taking? For 5 seconds, okay. That was really fast. Okay, for some reason, it doesn't usually does this fast. Has it read this file before? Yeah. Okay, let's try. Strange, why? It's not usually that fast, actually. Let me rerun this. I think it was cached in the memory. That's why it read this thing fast. Oh. Sorry. Yeah, so. Yeah, so this is relatively fast, maybe because it's a smaller file or something. And now I'm going to compare with this line here. I'm going to explain what I'm doing. Right. So, okay, so it's not big. It's not that much big of a difference. Okay, so this is okay. So I have something I need to admit. I have a high-end machine here I'm working on, right? So it's reading the CSV in 5 seconds. But when I did this project on another computer that did not have the same high quality specs as this machine I'm working on right now, it took much more than this. And right now it's 300 MB, this Excel file. So here to read it, it's taking 5 seconds, right? Versus this line, it's taking only 2 seconds to read the same data, right? I'm going to explain why. Okay, but imagine that this file was like 2 gigabytes or 3 gigabytes or 10. Imagine trying to read it. It's going to be definitely much slower, right? And that's when you need to work with a different file format other than CSV, because CSV is just a text format. You have a bunch of rows, and each rows represents some data, right? So this is where you need this file format called Park. Okay. And so what is Park or Parquet? So it's an open, so you can learn more about Parquet on this page, for example. You can just Google it. So it's an open source file format developed mainly to store your data in a compressed and memory efficient and performant format, right? So just to give you, just by comparison, 400 MB, 400 megabytes almost. The Parquet file is just 80 megabytes. That's it. So imagine the amount of storage saving. Now, probably here it doesn't make much of a difference, but in real life, guys, if you have like 1,000 of these CSV files, then imagine this, how much saving in storage are you going to get by storing it in this Parquet file, right? So this is a nice format, and the data is read much faster. Here it's 5 seconds versus 2 seconds, so it's not much of a difference. But on the long term, and when you have bigger files, that can make a huge difference, right? So always when you are working with larger data sets, even if the data comes in CSV, I always recommend read the data. Maybe it will take a minute, 2, 3, I don't know how much, depending on your data set, right? But then when you save it again, after you've done some cleaning, save it in Parquet. Or after the very first read, just save it in Parquet. So when you load it again to play with it or to try something again on it, it will load much faster, right? And so the way I do this here is, so here I'm defining where is my data and some columns. I split my columns because I am going to treat these columns in different ways. So I'm going to see if the file exists, right, using a try catch. This is not the best way, of course, but it's just one option. So if the file is found, I'm going to read the data from it. Otherwise, then I assume that the Parquet file is not there. So I'm going to read the CSV file, and then I'm going to store it into a Parquet file. So the next time I need to read the file, I read it faster. And this is going to save you a lot of time and effort, okay? So this is something, so the format is, yes, the format is Parquet, so you can search this format. And this pandas, so Excel, for example, does not, I don't think it supports this Parquet format. I'm not sure, right? But I don't think it supports this natively. But libraries, open source like pandas, do support these things, right? So it's good to work with such libraries. Okay, so this is one thing we were doing here. All right. So now I'm getting into the modeling. Okay, so the car maker and the model, they are related, right? So yes. So for example, let's go. So a Corolla is definitely a Toyota. If you hear, or Mercedes S500 or an S500 is a Mercedes. We know that there are no other manufacturers of S500 besides Mercedes, right? So rather than treating the model and the maker as independent columns, I'm combining them, right, to make them into one column. Okay, and this is what I am doing here. And I am also getting rid of some variables that I'm not going to be using in my model. So after I've combined maker and model, I get rid of the individual columns, and the dates the ad was created and last seen, I just get rid of these as well. And here is my data, okay? Now you might see like I am storing this data in another variable called tdata, and I'm deleting the original variable. This is because this three after cleaning, I think it came down to less than 3 million cards, but it's because this data variable can eat a lot of memory, right? So that's why I'm deleting the original variable data, okay, and I'm just keeping this transformed variable after I've done this. Okay, so let me run these lines here, and then get this line. So now let's see. So I have the type, okay, and then I have all of the other information, okay. Now, if you want to evaluate your model performance, you can't use all of the data that you have for building your model, right? You need to split it, right? So you take like 80% of the data to show it to your model if you want. And once the model sees this data, now it has acquired the knowledge. Now it understands how to predict prices, right? And then you're going to give it a test based on like the remaining 20%. So 80% for training, 20% for testing, and that's what I'm doing here. And for this, I'm using a nice function from this library SciKit-Learn. So it's time that we introduce the very famous library SciKit-Learn. So SciKit-Learn is a very big library. Here is the site. So this is one of the most famous libraries for machine learning. So, and using SciKit-Learn, you can do a lot of work on your data. Okay. You can install it just like you install pandas on Windows, and under SciKit-Learn you can find a variety of things if you want to do. So we have regression, we have classification. A classification, for example, a simple way to think of a classification problem is like real email versus spam email. So if you have some email, you want to judge whether it's real or spam. So you get a bunch of data, you show it to a classification models, then it can tell you like whether this is real, whether spam, and you can see how well is it doing on this data. So, and then you have regression, which is what we're talking about, and then you have clustering as well. That's another type of machine learning, basically for identifying, for breaking your data into groups without actually informing the model that you are giving the data to, whether these groups. So in classification, for example, you tell it which emails are spam, which emails are not spam. Or in clustering, you do something similar. You try to break it into two groups, for example, but you don't necessarily tell it which ones are spam, which ones are not spam. Okay, so it's a useful toolkit for you to know about. And so the function that I'm going to use is called train test split. All right, so I give it my data, I give it all the categorical string columns. Here I call them, they are the categorical variables. So these categorical variables are type, they are text, right? So, and we're gonna change them. We're not gonna keep them as is this way. We're gonna change them into numbers. I'm gonna show you how now, right? And believe it or not, it's not gonna be easy because we have, if I take data and if I look at type, how much is this? So I have 841 unique card types, okay? And here I'm talking about the type and the model. So that means that this individual column of type, I'm gonna convert it into 841 columns, okay? Why? Because machine learning models are models that deal with numbers, they are mathematical models, and in order for them to work on this data, right, we have to convert it into some numerical format for these models, right? So we'll have to change this type into a number, and I'm going to show you how. Okay, but let's just stick with the train test split. So I give it my data, I give it the variable of interest, which is the price column. I tell it I want 20% for testing, and then I set this random state variable. And you're going to see this random state variable a lot in machine learning. So most machine learning, so, okay, so how do I say this? So you have some data, you have 2-3 million cards. How do you pick like your 80% or your 20%, right? You pick it in a random order. So every time you're gonna pick something random. But if you want reproducible results, like, yes, it's random, but every time you pick like uh, a specific set of rows based on a given based on like what we call a seed, or let's say, so it's more of a controlled randomness, right? So as long as this seed or this number that I'm giving this method does not change, then every time it's going to pick exactly the same rows, right? And the reason you do this is just to be able to reproduce results, right? Uh, so if you run this code, if you exclude this line, you run this code, and another person comes and run this code, each one might get different results. So in order for you to be able to reproduce your results, you just set this variable called random state, and you'll find it used a lot in research and in machine learning. So of course, don't try to find the best seed to give you the best results. The purpose of the seed is just to be able to reproduce results, right? Don't try to find the best way of randomly selecting the data. There are alternative ways to selecting the data, mainly cross-validation. You can search the term. It's basically like shows your model, the entire data sets, but in different cycles. It will exclude the specific part and include the remaining part. So there are ways to do this, right? But don't just like rely on this random seed or random state, to try to find, because it's a random operation and you're just setting it here to get reproducible results. Okay. Then we're going to scale. All right. So certain models, particularly, so the price is a numerical variable, but it can always be positive, right? Certain models, when you train them, and you'll have to look into the mathematical formulation of the model to understand why this happens. But certain models, when you train them, they can give you negative prices, okay? Is just due to some randomness and due to the model trying to find the line that best captures in the data, right? So to avoid this, you just have to take the log of your price column, and this is what I'm doing here. And for numerical variables, right? Because for numerical variables, because they come in different magnitudes, so this is in the hundreds, this is in 1,000, mileage can go up to hundreds of thousands. So you want to scale them, all right? You want to put them all on the same scale, because if you leave them in different scales like this, then the mileage variable can influence your model, right, in a negative way because of the large magnitude of its values. And when it does that, you don't necessarily find the best line. So you want to put all of these on the same standard scale. And the way you do it is you subtract the average of this column, and then from each value, and you divide by the standard deviation. If you've taken some statistics course, you'll have an idea of standard deviation or variance. So it's basically how spread your data is, right? Is it too spread, or is it like concentrated in a small area? So that's variance and standard deviation. So you can also search these online. They are not a difficult concept. But the idea is when you scale them, you'll put them all in the same scale. Now here is the thing. This standard scaler, again, is a scikit function or a model itself for scaling your data. And this is quite important, guys. when you scale your data, you only scale your training data, right? So you calculate the mean and the standard deviation based on the training data. You don't calculate it based on the training and the test data. Why? Because that can influence the score or the performance of your model. It might give it a little bit of a boost, right? Because you are giving some information from the test data to the model indirectly by scaling on the training and the test. But ideally, in the real world, when you feed a new entry or a new data point to your model, then you're going to apply this scalar, right, or this method of scaling the data uh, using the mean and the standard deviation you captured from your previous data, right? You're not gonna recalculate your mean and standard deviation when you see new data points. So ideally, what you want to do is you want to imitate this process here when you are building your model and trying to find out which one has the best performance. When you are almost done, then you're gonna assess everything. Then you're going to train your model on the entire data set and deploy it to the real world. But when you are trying to understand which one does the best job, then you want to try to imitate the real world scenario, right? So you scale the data on the training only, and then you find that use that mean and standard deviation calculated from the training data to scale the test data. What have we done here so far? Now there is this nice art. So now we come to one-hot encoding, right? So there is this nice article, and you can search it. A fast one-hot encoder with SciKit-Learn and pandas. I'm going to explain what's one-hot encoder or what's one-hot encoding. But the one that comes with SciKit-Learn is not great. So this article explains how you can build a custom one with scikit-learn and with pandas. And this is what I did, and I built my own method. Right. So let me just show you something. So I have xtrain here. So I have this type column, and now after I do my one-hot encoding, right, you're gonna see the difference. Voila. Now, as you can see, and ignore this column for a moment. Type Alfa Romeo 145. So false, false. This false is a 0, guys. Okay. This false you are seeing here is a 0. So in computer science, false is like almost equal to 0. Okay. And true is 1. Okay. Most programming languages treat false as 0, and they are not the same thing. This is a Boolean, and 0 and 1 can be integer, could be bit, but most programming languages will treat false as 0 and true as 1. So what you are seeing here, right, are basically zeros, right? It's just a display. And so what happened here? So what this function did, or what one-hot encoding does, is it takes this type column, identifies the unique values. So we said we had 814, and then for each value, it will add one column. And if a specific car belongs to that type, then it will have a value of 1 or true in that column. Otherwise, it will have a value of 0, right? And so if I want, yes, and I'll show you here an example. So as you can see, this I've done a filtering here. So I'm telling I'm telling pandas, give me the cars where this column has a value of 2, or basically this column has, or the cars that are in these rows are of this type of car, right? So I can do 145, 6. So 145, 159, for example. So these are different types of cars. I mean, they are just showing here based on like numerical, alphabetical, I think, yeah, alphabetical order. And as you can see, I have 142 of these cars. Right. Now, the problem with this data, okay. So you have around 2 million cars, right, and 900 columns. Okay, take this data, feed it into any machine learning model, and it's going to scream. It's going to ask for so much memory to compute, to learn from the data basically, and compute its parameters, whatever it's trying to find, to be able to predict prices. So it's gonna scream, right? At least not in this format. So what are we going to do? Now you realize maybe of this car we only like have 100 cars. So I have an entire column, 2 million values. All of them are zeros. Almost all of them are zeros, except for just 100. Right? So if there is an efficient way to, for example, store this column, yes. And that's what we call sparse format. I'm not sure if you have heard about sparse format, but for example, essentially, so for example, let's say I have this column of zeros and this column of ones, right? Let's say like 2 ones. So instead of storing like in the first value is 0, second value is 0, third, and so on, I only store the index. So this is, let's say for example, this is in row 12, I have a value of 1. The way that a sparse format stores data is it doesn't store all of these values. It's going to turn a blind eye to the zeros, act like these zeros, they never exist, and only store the ones. So in row 12, there is a value of 1. In row 13, there is a value of 1. And that's an efficient way in terms of memory and in terms of size of storing your data. The reason we need this format is because we one-hot encoded this data, right? That's why we need this format. And we applied this not just to the type column, we applied it to the seed count, right? We applied it to the fuel type, and so on. So that's why we ended with 900 columns. Right? And you can search online how to convert your data to sparse format. It's not difficult. It's fairly easy, and this is what I'm doing here. And then after I've converted everything to a sparse format, okay, so as you can see, sparse matrix of type NumPy float. So NumPy is another library like pandas, but it's more for mathematical manipulation. Okay. So what it's saying here is it has a sparse matrix. So what is this sparse matrix? Let's take this, throw it into Excel. Let's see what Excel says. Okay, so we have 2 million, right? 2 million. 2 billions actually. Yeah, 2 billions. Yeah, pardon, not 2 millions, 2 billions. 2 billion values. So the matrix size is 2 million something by 913 columns. So I have 2 billion values. But out of these, how many are actually stored in the sparse format? 19 million only. So imagine the saving. So from 2 billion to 19 million. That's a lot of saving in terms of memory, compute, and everything. Okay. And this is the benefit of converting everything to sparse. Dimensionality reduction is a way of summarizing your data. Okay. And I'm cautious here about the time. So you can learn more about dimensionality reduction if you want. But what I'm doing here is, instead of keeping all 913 columns, okay, I don't want all 913 columns in my data set. Okay. So how do I summarize the information that is stored in these 913 columns in a way that preserves most of the information? So imagine you have a paragraph, like 1 page, 2 page, 3, not a paragraph, no, maybe like an article, 2 pages, 3 pages, and you want to summarize it in a single paragraph, okay? And that's the goal of dimensionality reduction. And it's named dimensionality reduction because in this sparse matrix, okay, I had 2 million rows and 913 columns, all right? Not all of the values are stored. I stored only the non-zero values, but I can even reduce this data set even more. Like, get rid of these 913 columns, and for each data point, capture the most important information for each data point and for the entire data set using this technique called dimensionality reduction. So dimension means dimension here, the word dimension translates to number of columns, right? The most famous dimensionality reduction method I know of is PCA. Here I'm not using PCA because scikit-learn implementation of PCA does not support sparse matrices, and there is a reason it doesn't support that. You can, if you look at the documentation, you'll understand why. But I'm using another method called truncated SVD, which is sort of the basis of PCA, or principal component analysis. It's just, again, a way of summarizing your data. So now, after I've done this dimensionality reduction, okay, I'm going to have a matrix right here. Here it says array, but if I show you shape, it's a matrix of 2 million rows by 6 columns. So I got rid of how many? 907 columns, because again, most of these columns are of this type, right? True, false, that indicate different pieces of information. Originally, I didn't have that many columns, right? Now, the benefit of dimensionality reduction, it improves model performance, right? Number one. Number two, and it gets rid of the noise. So sometimes your data is too noisy. It has lots of irrelative information in it, so lots of randomness if you want. So when I do dimensionality reduction, I can do that. And you can learn more. I think you can learn more here on the website of SciKit-Learn. They have a specific section here, and they explain like PCA, principal component analysis, what it does. So if you read this, then you will get an idea. And this is done on human. Might be a little bit scary, but this is done on human faces. So you basically take a picture of a human face, and you just capture the most important features of it, right? So you can learn more about it here. Okay. And then we come into modeling our data. So here is an algorithm, is called SGD regressor. Okay. The benefit of this algorithm, I'm not going to go into much details, is so you can, if you continuously keep getting new data, you can train your model, okay, using this SGD regressor, on what in the initial data you have, and then once you get new data and you think this new data can impact your model performance, you can use this regressor. So it supports what's called online learning. You just keep fitting every time you get data, and you keep showing it the new data. And this is a chart. It plots the actual price versus the predicted price for this model. And ideally, what you want to see is a straight line, is a diagonal line like this, right? You don't want to see this. So you want to see a diagonal line. And this model explains its R squared is 0.6, so it explains 60% of the variability of the data. So it has a benefit of supporting this online learning. Like you can keep, you can, and you don't have to retrain it on all of the data. So you got like 1 million rows today. You train it on the 1 million. Tomorrow you get like 200,000. You train it again, or you show it only the 200,000. You don't have to start from the beginning and show it the 1.2 million rows, and then after tomorrow you get another 100,000. So you just show it the 100,000, and again you can look at the documentation of this model to see how it works under the hood, how it's able to do this, right? To understand more. And here is the performance, and here's some of the actual price. See the actual price for this car, it's 1900, it's predicted 3000. Here it's 13,000, it's predicted 11,000. So yeah, it's not great, but it can get few points close, few points it misses, like this one, 6 to 50, it's predicting 12. That's a big difference, for example. So this is something that means that either the model is not okay or there's an issue with the data. Someone asks, like, how do you know whether I've done good cleaning or good modeling? Then this is one issue. The actual is 6, but predicted is 12, right? And so these models, so all machine learning models have some parameters or have, let's say, some conditions of so some conditions. Just a moment, guys. I think I'm getting a message. Oops. Guys, there is a form here. I didn't realize that. Oh, this is a long form. Yes. I think there was a form that I was supposed to share with you guys. I unfortunately did not share it. I wasn't paying attention to the messages in LinkedIn. Sorry. Yes, there you go. Yes, so I think you guys need to fill this form, this Google form. This is the attendance form, so or registration form. So please, please register in this one, okay? Please register. Apologies, Dr. Heber, for not noticing my LinkedIn and sharing this one. All right. So please register in this form, guys. Okay. And so this is not a good prediction, right? So sometimes you can play with the model itself. So if you go online here in SciKit-Learn, yes, you will find a lot of parameters for these models, right? Or some assumptions of this model. Now, if you understand, if you take each model, you go into the mathematical formulation. If you go into the mathematical formulation of each form, then you'll understand what are all of these things, right? But usually you can play with, for example, the penalty for regression to like find a better model. So here I do some. So here I do some manipulation, and unfortunately I don't get a much better result actually. So I had like 0.6, and after trying to find something better, playing with the different models, I get 0.57. So not much of a performance actually, so still have the same issue. All right, and then I try it. So this was done on the original without the dimensionality reduction. Okay, yeah, not great. When after the dimensionality reduction, it's not doing great at all. It's just 0.35. Okay, now for the sake of time, I'm going to show you the best model that we had. So in machine learning, usually you will try a variety of models, right? You're not just gonna test. You're not just going to test one model, you will try a bunch of models, and then you will find the best one, and then you try to tune it, play with the parameters to find the good performance. So here is the model, k-neighbors regressors with truncated SVDs, the dimensionality reduction. So this k-neighbors regressor, you can apply it on the original data, but because of the original data is so large, like 900 plus columns, it's hard to apply it on. It's hard to use this k-neighbors regressor on the original data, so you have to reduce the dimensionality. Otherwise, your computer is going to ask for like 120 GBs of data and like take like 10 days to train the model or something. So it's not feasible, and that's why you try to reduce the number of columns in the data, right? Using whatever dimensionality reduction method. So k-neighbors regressor. Now I'm gonna do a silly sketch again. So what does k-neighbors regressor does? So imagine we have, so let's say engine power here, okay? And I'm not good at drawing, guys. So, and then we have doors, number of doors here, right? So we only have 2 dimensions or 2 columns in the data, and then we plot a bunch of cars. Right. So I have a car here. So I have a car here. I have a car here. I have a car here. I have another car here. Right. I have another car. Then I have like another group of cars here. Then I have another group of cars here. Then I have another group. Another group here. Now, of course, this is an oversimplification, right, of the problem. Okay, because I have only 2 columns. But the assumption of this k-neighbors regressors is that these cars, right, should have a similar price. These cars should have a similar price. These cars as well. So if I get a new car, and let's say when I plot this new car and it falls here, somewhere here, for example, then I'm going to take the average price of these cars that inside this circle, and I'll use the average to predict the price for this new car. That's the idea behind k-neighbors regressor, okay? And this is the best model that we have. If you've heard about neural networks, neural networks surprisingly didn't do well compared to k-neighbors regressor. Okay, so this algorithm turned out to be quite awesome. Okay, and that was the best performance. And look at the difference. See, in the previous, so the actual price, you can see that is related or correlated with the predicted price, and that's why you see this diagonal line, right? Except for a very few rows here. So this is something that you want to take a look at, but generally they are correlated. As the actual price increases, the predicted price increases. So there is a positive correlation, right? So, and the reason we create this type of chart is to see how the model performs. If you look at the previous chart, so the actual price is increasing, but the predicted price is not necessarily increasing, right? So then you know that there is something wrong, okay? But for this model, you can see that both are increasing. So this is the good news, guys. This is a very good model, right? It can explain 88% of the variance or the variability of the data, or it can capture 88% of the information you have in your data set, right? So this is a pretty good model, right? Now, because this is the best model, right, we have found, I'm going to walk you through the model a little bit. So now let's go back to my sketch. So obviously here you have a problem. Right? Here I made it quite obvious, but let's say, for example, okay, I'm gonna draw something different here. Okay. And then I'm gonna draw other ones like real close. So now my question is, do you consider all of these as one group, or do you consider these as one group and these as one group? That's the question. And this is what this parameter called n neighbors, number of neighbors to use, is designed to deal with. And believe it or not, there is no magical formula for this. Okay, this is something you will have to try different values and pick the best value, or the value that provides you with the best results. And there are ways, for example, to measure how good of how good is this number. Okay. Because in reality, what this model does, it will try to find like a center for these points. So these points, let's say, for example, their center is here in orange, right? So their center is here, and consider this like one group, for example, something like this, and these are one group, or like, for example, I'm looking at this point and I'm considering the nearest 5 neighbor, and the nearest 5, for example, are going to be this, this, and this. So it's a measure of distance. Okay, it's a measure of distance between each point and the neighbors and the neighboring points. So which points are closest to a specific point, and then based on that, it tries to predict the price. Okay, so here, this is the number of neighbors. Weights. Okay, so this is another important one. So uniform weights. All points in each neighborhood are weighted equally, right? So imagine we have quite a big of a neighborhood, for example, like this one. Okay, like this one. These points, you have them together here. Okay. I'm just gonna delete this one. This is getting messy. So we have this quite big of a neighborhood. So yes, okay, so I know that this point, its neighbors, the neighbors for this point are these 4 points. Okay. But how should I give equal weight to each of these points, or should I weight them by the distance? Okay. Now, the closer the points are to this point, so imagine I had another point here, right? Imagine I had another point here. So do I weight all of these points using the same, do I give them the same weight, or do I give this point more weight because it's closer to this one, right? Is it closer to this one? Yes. Give it more weight because it's closer? Yes. And that's what we choose, actually. Do it based on weight. So uniform weights, all points in the neighborhood are weighted equally. Distance, weight points by the inverse of their distance. In this case, closer neighbors of a query point will have a greater influence than neighbors which are further away. Or you can even define your own custom function if you want. Okay. And that's what's cool about SciKit-Learn. And algorithm is the algorithm used to find the nearest neighbors. Okay. You can, because I don't think we have like enough time to walk over these, but these are a different story on their own, so you can read about it. Power parameter for so the distance here, if you so the measure of the distance, like how do you measure the distance between 2 points? And there are different measures of distance, so Euclidean distance or Manhattan distance. Okay, so you can learn more about this, but let me give you a quick idea. So I have, let's say I have 2 points here. Let's say I have 2 points here. Okay, these points are like this. Okay, so Euclidean distance is just the shortest. No, let's do that. Oh, it's the brush. So this is your Euclidean distance, shortest distance. Manhattan distance is this. This is Euclidean distance, shortest line, right? Manhattan distance, another measure of distance, is the distance from here to here, and then the distance from here to here. So it's just how you measure the distance. Now, this Manhattan distance is good for real world, like Google Maps. Surely they calculate Manhattan distance. They don't calculate Euclidean distance. But you have to test, try and see which one performs better. And if you have a good computer, usually this model, when it's training, it will run on one CPU. So you can adjust this in jobs parameter to make it run on more CPUs. So for example, if you give it -1, it will use all the processes. Now, of course, this is something you want to do because it will be faster, of course. And here, after tuning this model, we came up with the parameters. So the best one, there is something called grid search cross validation. So grid search cross validation, it's just you tell it what model to try and which values to try. So for the distance, I told it 1 is Manhattan, 2 is Euclideans. Weights, I give it uniform and distance. The number of neighbors, I give it from 20 to 23. Okay. Ideally, you should increase the range like from 2 to 100 or something, for example. Number of jobs, I give it 14, like run on all CPUs. And cross validation, CV5, this is something related to cross validation. I don't want to spend too much time on it, but essentially this is a way of finding the best parameters. So 21 neighbors with a Manhattan distance, and you give more weight to the closest points. R squared 88%. So as you can see, like almost perfect. 1900, 1900, 1385, 12, 683, 8, 6, 16, 16, 6 to 56, 530. So much better predictions, much better predictions. Okay. And actually, this is a very good number given that this data set was pretty missing. And here you have the chart. The nice thing about this, what am I doing here? Yeah, I think it's the same. There are other algorithms called XGBoost and XGBoost. XGB is a good algorithm. You might want to do a little bit of reading on that. And it did well at 77%. Okay. And there are measures here, MSE, MI. These are numbers, basically, actually, the difference between the actual and the predicted, right? And the bigger this number, the worse the model performance. So MSE is mean squared error. So you want this number to be lower and R squared to be higher. Okay. So this XGBoost did a good model. The best model is this key neighbors regression. Okay. And here I do something nice. So this is a test point. So I give it a test point. I give it one test point. And I see like what is the price and what is the predicted price. The nice thing about this k-neighbors regressor is that it's going to tell you what are the neighbors. So model, how did you know that this car price should be 3961? Okay. So, well, sir, I looked at all of its neighbors, and you can see. So this is a Fiat Punto. manufacture year. So you can see like 2009 manufacturer. So you have 2011, 11, 12, 9. We have 2006 and 7. Engine displacement is almost close. Mileage. Yeah, this is not a perfect this one because mileage is not there. Okay. Compact. These are all compact cars. All right. See this. So these are issues. So yes, essentially we decided to keep such data points with no mileage, no fuel type. But in real world, you might want to try to find a way to get all of this data. The more data you have, the better. Okay. So, but what I'm trying to say is this is the point, and these are its closest neighbor, and it even shows you what's the distance, right? What's the distance from this? So the lower the distance, the closest is the other points to this point, and you can see like what are the characteristics. So you can. This is a way for you to understand how is this model predicting this much price? Which points is it taking into consideration? And so on. That's it. Is there is a way to fine-tune this model more so as to get better than 88%? You have to handle issues in the data, right? This is one. I don't think there are other parameters to play with. I think is the more accurate the data is, the better. And you may want to do something. You remember if I talked a little bit about clustering, SciKit-Learn. So clustering is basically if you take a bunch of data points and you want to know which points are similar to each other, right? You don't know which points are similar to each other. You want the computer to find this for you, right? So you might want to do something like this. Is you look at the points just like what we see in this image, and you find that these points are close to each other, these points are close to each other, so these are one cluster. So one thing you might want to do with k-neighbors regressor is after you've done clustering, feed the same data to the model and find out whether there is a specific cluster or a specific group of cars where the model is not doing well, right? So this is one way where you might say, okay, fine, this model is not doing great for this group, so let me take this group out of the rest of the cars data and build a special model for these. That's one modeling technique. So essentially, you are not tuning the model. Is you're identifying that that the model is doing well compared to others, but on a specific group is doing a terrible job. So you either go and see the reason it's not doing well on this group of data points, or for example, you go and build another model for that. I hope that makes sense. Yeah, I think this is. Yeah. Let me actually. So yeah, please feel free to post any question. Oh, all right. So minor tweaks within the data before feeding it is the way to go. Yes, yes, and also finding outliers. Maybe your data have some outliers. So that's something that I didn't talk about. That's another thing, and that's another topic on its own. So here you have, I think, outlier detection. Outlier, some novelty and outlier detection. So outlier like are unusual points within your data. So you might want to take all of these outliers. If they are good points, valid points, you might develop another model for them. And if they are not good points, then you just discard them or something. So outlier novelty detection. So this is something you might want to consider. And this modeling is an iterative approach. Now, obviously, in a course or in a limited time project, you will have to stop at one stage and say, okay, fine, this is how much I can achieve. Now, this is course project, so we had a deadline, and also whatever we managed to achieve, we've done it. But in real world, this is an iterative process. You start with something, you do some work, then you arrive at a result, then you go back, and then you repeat, try to find a better model, a better way of characterizing the data or capturing information, and so on. All right, guys, any further questions? So I know the stream went a little bit beyond what's scheduled. So we were planning for 1 hour, but I didn't want to cut too much information from you guys. So we had to go 1.5 hours. Anything else? Any questions? All right, so I think that's it for today. You're most welcome. Most welcome, Islam. And have a great day, guys. And if you want, thank you. Welcome, guys. If you want, you can ping me on LinkedIn. That's my profile. You can send an connection request. You can search here for you guys in the chat. You guys can ping me, send a connection. I'm happy to connect with you guys. If you have any questions, as well as you are embarking your data science journey, feel free to send a message. I'll try as much as I can to respond, and I wish you guys the best of luck. Thank you for attending this live stream.